Welcome back to Medical Engineering. Today we want to continue talking about magnetic resonance imaging, and in particular we want to figure out how to use the magnetic resonance effect in order to actually calculate images. And you will see that this is actually a very nice application of the Fourier transform. So looking forward to be exploring the actual image formation in magnetic resonance imaging with you guys. So this is today's outline. We want to explore the principles of magnetic resonance imaging, the slice selection, the spatial encoding, and then we want to explore the so-called K-space. So K is the wave number, and we want to explore the space of wave numbers. Then we see finally a comparison of slice selective versus volume selective 3D imaging. And then in the second part of this video, we want to talk about advanced applications like spectrally selective excitation and functional imaging. This is already something that I hinted in the previous video. So let's start talking about the principles of magnetic resonance imaging. And now we really want to talk about the imaging. So you see it here in red. So this is actually the part where we explain how to get the images. So far we excited all of the nuclei at the same time within the magnetic field. Now for imaging we need spatial information. So we think about how to actually get the spatial properties out there. And there's two concepts, that is the slice selection and the spatial encoding, and both of them will be used in order to figure out where actually which information is coming from, and both of them are based on the gradient coil system. So let's have a look at a cut view of such an MR scanner, and here you can see what would happen if we would cut the scanner open. Well, of course, first of all we would get a huge quench, so all the liquid nitrogen would actually emerge. But obviously this is just a schematic. So what happens here is that you have the radio frequency coils. So they are actually inside here in the coil system around the patient. Now you also see how deep the scanner is. We can fit the entire person in here. So this is our patient. And we've already seen that there is a patient table that is used in order to move the patient inside here. Then there is the main magnet. So this is our main magnet, which is the strong magnetic B0 field. And we have the so-called gradient coils. And the gradient coils here are the ones that we use in order to steer the direction of the local gradient field. So why do we need these gradient coils? We've seen that we have the RF coils, so we need them to excite and to read out. But now what are these gradients for? So the gradient coil system is a kind of system that allows us to modify the strength of the magnetic field locally. And there is in principle 3 coils. So there is the so-called Z coil that allows us to increase and decrease the magnitude of the field in Z direction. Then there is the so-called X gradient field. So this changes then a stronger and weaker kind of magnetic field in X direction. And we have the Y coil. So the Y coil then changes the strength of the magnitude in Y direction. And with these 3 coils, we can then essentially superimpose them over each other. And this allows us to get an arbitrary type of change in the local B0. And this can help us to change the Lamer frequency at every spatial position inside of the scanner. So if this is then implemented, you can see here that we have now in a different color, of course, than on the previous slide. So this is our X coil, and these are essentially coils, and they can introduce an additional magnetic field in this direction. The Z coil would introduce it in this direction here, and the Y coil would introduce it in this direction here. So you see with our different coils, so actually I should use this color here. So let's use this color here. So this is our Y coil. So we're able to apply additional magnetic fields in all spatial directions, and this is the gradient system. By superposition of them, we can essentially guarantee additional magnetization in any orientation. And this is also the key component why we can apply these gradients in all directions and therewith acquire images in all possible orientations. Let's go ahead and talk about the so-called slice selection. Now, slice selection is the concept that allows us to select only a specific slice within the body. And the idea is that we want to use the gradient in order to apply some additional magnetization, Z, and this allows us to adjust the Lamer frequency of the respective voxel. So if you do that in Z direction, then the additional Z coil would increase the frequency towards the feet and decrease the frequency towards the head. Now, because we excite only with a specific frequency and we can pre-compute that, we can see that this would then align with a specific position in the body. So the gradient can be used to select only a specific slice within the body. And of course, with superposition of the different gradient fields, we will be able to actually get any kind of orientation here. So how would we do? Well, we would pre-compute at what frequency we actually have to excite. Then we apply a specific gradient, and of course we do that with the right steepness. And we know that maybe we are exciting a little more because there's some co-excitation of neighboring frequencies, but we can then map this very nicely to a specific area within the body. So you see, this way I can essentially determine by the steepness of this gradient, I can determine how thin the slice will be, and if I take a direction that is more broad, then I will get very thick slices. And with this idea, we can then essentially determine which slice inside the body will be excited, and therefore all the signals that we are measuring, they can only emerge from that particular slice. So you see here, I have the neighboring directions that are being excited, and this means that with our particular gradient, we will only select voxels that are actually lying in this region of the body. So this way we can get an arbitrary slice excitation. Now we have to go ahead and somehow figure out where the signal is coming from within the slice. And this is called spatial encoding, and we will use some additional ideas that we can actually use again the gradient coils in order to introduce something which is called phase shift. So how does this work? Well, typically if we excite uniformly, then all of our hydrogen nuclei, they will spin in exactly the same phase. So we excite them uniformly, and then all of them will essentially rotate in synchrony. So we cannot use the slice encoding principle again, but we can use a trick. We use again the gradient coil, and then we again introduce a shift in the Lamer frequency. So what we can do is we can essentially change the local magnetic field after the excitation. After the excitation, all of them rotate in synchrony. And then we want to change the magnetic field locally such that some of the rotations are out of synchrony. And this is then called the phase shift. So this kind of angle between the rotations is the kind of means that we want to use in order to differentiate different spatial positions. So how can this be done? Well, let's start with a one-dimensional example. And now we encode, let's just stick with the 1D example, and we excite everything, and then depending on the magnetization, the number of hydrogen nuclei within the voxel, we will get a different net magnetization. You see here we have many, and here we have fewer, and here we have many of them again, right? But they all are oriented in the same direction because we excited them in the same phase with exactly the same kind of RF pulse. So directly after the excitation, all of the spins have the same phase. They all point into the same direction. Now, if I were to measure, what I would measure from this set of voxels is essentially a sum. I get the superposition over the actually in the entire 2D slice, but let's stick with the 1D example first. My measurement is not able to resolve spatially. So I get the sum over all these net magnetizations, and this then, because they all point in the same direction, this gives us a net magnetization that now points towards the top. Now, if this is done at a later point in time, that's not a big problem, because they all rotate in synchrony. So if I measure a little later, I might be measuring this here, but the magnitude is exactly the same. It might be a different orientation, but the sum will cause the magnitude to be exactly the same, and because everything is rotating in synchrony, I always get the same signal. So there's not a big problem, and they all precess at the same Lamer frequency, so we always get exactly the same magnitude but a different orientation, and all of them are of course oriented in the same direction because everything has been excited at the same time with the same frequency. Now we can use a trick. We apply a gradient field, and we apply the gradient field shortly after the excitation, and this then causes that right after the excitation we have a different gradient field. So they are already excited, so we know only the spins within the slice are actually already spinning, and then we apply this additional weaker gradient field. And you see, if I apply this weaker gradient field, I'm changing the local Lamer frequency. And by changing the Lamer frequency, they will start spinning at different speeds. Right? Because the Lamer frequency is different, then they slightly go out of phase. So if I now observe at the same point in time, but I apply it in between the weaker gradient field and the higher gradient field at this point, you see that they will be in a different phase. They will be rotated towards a different angle. So I apply this gradient field, then I turn it off, and then I measure. Now, after turning this off, everything will continue spinning synchronously, so I would again be able to measure the same magnetization in different directions because I kind of turned it off. So this net magnetization here will not change anymore. But now, because we orient the arrows in different directions, the sum will now no longer sum up to this large magnetization as we had previously, but it will be reduced. And now I can play with this kind of gradient and see how I can modulate the net magnetization of my vector. So this then could be employed with different kind of magnetic fields. So let's say I take a gradient that is stronger, so I have a stronger magnification or amplification here towards this side. Then you see in every time step we have a slightly higher degree of rotation, so we have a higher phase shift in every step here towards the stronger gradient. So we tilt a little more and then we measure again and suddenly our magnetization is 0. So if I have this kind of weak gradient field, I have a slight reduction, and I have this strong gradient field, then I have a stronger reduction. Now you can see that the arrows here, they kind of form a pattern, right? So you could argue now that if I did these two measurements, then I essentially I could plot the gradient field strength here to the right hand side and the magnetization here to the top. Obviously, without any additional gradient field, I get the highest magnetization simply because everything is in synchrony and I have no effects of the neighboring voxel that they disturb each other. Now, if I start applying a weak gradient field, I start reducing the signal. And you can see then, over increasing the field strength, I get this kind of lobes. So I'm jumping up and down with the field strength, and I generally have a reduction here in the general magnetization. But I can do this with repeated measurements, and I get this different kind of resonance effect because I caused a different phase shift. Now, why would I want to do that? Well, you kind of can think of this phase measurement as measuring parts that are kind of in the same kind of orientation. Or you could even put it into a kind of interpretation where you have a certain kind of influence. So you could argue that if I have a pattern, then I can essentially interpret it as I'm tilting them into a different direction. And if I would not have any hydrogen nuclei here, then I would not measure this part of the signal, right? So I would only measure the hydrogen nuclei that are essentially in phase here. So you could say that if I have a certain spin, then this gives me a pattern of rotation, and by measuring, I kind of measure the agreement of the magnitude of rotation with the actual observation here. And you see that we will get a higher agreement if we have a better match. So if my underlying pattern is this here, and I have this kind of orientation in my actual signal, then I get a very high excitation, and if the match is not so great, I get a lower agreement. We already described something similar when we were talking about correlation of signals, but let's make it a little more clearer. So what we are essentially seeing here is the agreement with the kind of phase shift along the gradient field strength and how strong this agreement is. You see, this is this curve here. So if we apply different gradients, we kind of apply different patterns, and by measuring, we pointwise multiply them and add them up. So this is measuring the similarity between the pattern and the actual voxel configuration. And now I get this trace, and the trace here describes essentially how the strength of the different orientations is encoded in the actual voxels. And actually this guy here is an intermediate representation of the image. So if I know this trace, I can reconstruct the entire information that was in my set of voxels. How? Well, let's think about this a little more. So what we actually have is not just the binary patterns as we've just seen, but you can think of this as a kind of intensity pattern. So you could say, here I have a strong orientation towards the top, to the bottom, to the top, to the bottom, to the top. So I could also encode the gray values in the following way here, right? And you see we kind of get this sine wave. And if I have a fast pitch, then I'm essentially getting such a kind of signal. So we get a sine wave with a very high frequency. This is interesting. Now we have these waves coming up here, but as intensity patterns. And if I have a lower phase shift, then I have a slower gray value transition. And if I have a higher phase shift, I have a stronger gray value transition. So what then happens is that these two signals, I can actually describe them as sine and cosine signals. So our phase shift here can be described as this complex composition of sine and cosine waves. And now you can already figure that out. What we are measuring is the integral. So this is essentially the sum of the signal pointwise multiplied with each other, and then all of the summed up. So we have this e to the power of ikx times f of x dx integral. We've seen this guy before, right? Striking similarity. And, well, yes. What we measured here is exactly this integral of a sine wave with the actual function that we seek to measure. We've seen this before. F of x is just the Fourier transform of mk. So what we are actually measuring is the Fourier transform of whatever we want to reconstruct. And if we know that we have the Fourier transform, we can apply the inverse Fourier transform, and then we get exactly our f of x. So the MR measurement does nothing else than acquiring the Fourier transform of the image that we want to reconstruct, and the inverse Fourier transform then gives us the original image. Now obviously what we've seen so far is only a 1D example. Now obviously we can also do this kind of gradient orientation with a 2D case. Then you get a gradient in x and y direction, and if you're superimposing these gradients, what you actually end up with is a kind of plane wave. So you see that we now have oriented waves here, and you could see that this is a kind of, you see all of the valleys and so on, they are aligned here. So we're getting a kind of plane wave, and if I play with the gradient directions, I will be able to rotate this plane wave, and I will be able to adjust the frequency or wavelength of this wave. This can be applied with the different combination of the gradient coils in 2D directions. Now if I do that, then I end up measuring n-dimensional Fourier transforms. So I suddenly get now here a scalar product and it's the orientation of your wave and the inner product with the actual configuration at this voxel, and then I can measure the phase pattern in that way. And this then leads to n-dimensional Fourier transforms. Now let's not talk about the n-dimensional case, but let's talk about the so-called k-space. And the k-space is essentially typically a 2D generalization or 3D generalization of that. So this is a 1D k-space here, and this is the 1D Fourier transform of the actual image. And in 2D the whole thing looks like that. And we've already seen that when we talked about the Fourier transform in the image processing. So here this space again is characterized by the orientation of our wave. So the k is the wave number, by the way. So we can essentially determine the orientation. If you have a point here, then you see that the wave is oriented in this direction, and that the distance to the center encodes the frequency. So the closer you go to the center, the more you will have distances between the valleys and the hills. So this is a longer wavelength. And now if I go towards something like this is maybe oriented in this direction, and then you see that I have a high frequency here, and that this is a wave that is oriented in that particular direction. So here this is the orientation direction, and then the further I go to the outside, you see here I have a already pretty high frequency. You see that this is essentially oriented in this direction, and we also see that it's further apart from the center, so the frequency is also higher. Now what I actually measure is this kind of signal pointwise multiplied with the image that I want to measure, and then I sum up over the entire field here and write this value here. And if I want to measure this point here, I take my input image, multiply it with this image, sum everything up and write it into this value. And if I want to measure this point, I take this kind of plane wave, multiply it with the entire image pointwise, sum it up and write it here. And to compute this point, I'm summing up everything, so first multiply pointwise with this plane wave, summing up and write it here. So this way you can construct a 2D Fourier transform. So maybe if you haven't understood the concept in the previous video, maybe this helps to understand the 2D Fourier transform. If you want to reconstruct this image, what you take is for every pixel, so let's say this is your image. This is what you want to reconstruct. If you want to reconstruct this pixel here, what you have to do is you have to take essentially all of the points of the Fourier transform, multiply them with the corresponding plane wave, all of them, and then you look into this position, and then you sum them up here. This gives you this result. So if I want to go from the Fourier space, I essentially have to instantiate all of these plane waves, I multiply them with the respective coefficient, and then I sum all of them up in order to form the original image. So this would be an inverse to the Fourier transform. So we always need this kind of basis in order to construct it. Going to Fourier space is taking one plane wave, multiplying it with the image here, and writing it into the vector. And going back is taking all of the points here, multiplying them with the respective base functions, and then adding everything up in order to get the image again. So this is how you construct a 2D Fourier transform and its inverse. Very well. now that we are able to measure all of these points, of course, we can also reconstruct it. There is one more trick that you can do. Instead of only using 2D planes, you can also excite entire volumes. So what we just discussed is the so-called slice selective encoding. I'm selecting slice by slice, 2D spatial slices, and then I compute the k-space within this slice and reconstruct it. In contrast to that, you can do the volume selective one, and there you encode essentially a 3D k-space. So now you take all of the free gradients in order to construct the plane waves. You don't need the slice selection. Well, you probably still need some slice selection, but it's a volume selection pulse because you're computing the entire volume. So you excite in every step the entire volume. Then you perform a 3D spatial decoding. So we now have 3 orientations of the plane waves. That also means that you have to acquire more of those points, right? And more of the orientations because you're now sampling a 3D k-space. But if you think acquisition-wise, if you have the n slices or directly the 3D k-space, maybe not so much different. Then one characteristic that you typically get is you get the isotropic image resolution, and you have an inherent SNR benefit because more nuclei are excited and resonate. But obviously you probably have more excitation to do, because if you want to have an isotropic resolution, you have to choose the same number of slices in every direction. Otherwise the resolution will not be isotropic. So this then means that you probably also have to acquire for a longer time if you don't have any kind of differences in the resolution in that direction. So this is why quite commonly the slice selective ones are used, because then you choose thicker slices in one direction and then sacrifice this for scan time. So that's a difference between volume selective and slice selective. Very well. Now you heard about essentially all the basic imaging techniques, and we learned that our friend the Fourier transform is a very important feature here. Then we can go on towards advanced applications. And the advanced applications that we want to discuss is going beyond simple morphological T1, T2 proton density imaging, as we discussed in the last video. Then we also want to look into spectrally selective excitation. And there you can use, for example, T2 preparation pulses and water-fed separation. Or you can go towards functional imaging, where you then use non-contrast angiography or bold imaging. Very advanced techniques. So let's continue talking about this. And the first thing that we will talk about is the T2 preparation, for example, for coronary angiography. So there you want to improve the contrast between the arterial blood and the myocardium. And this relies on the difference in the T2 constants of the two. So there's actually a change in T2 if you have arterial blood and if you have blood that is venous. So this allows us to play with those effects, and what we want to do is we want to decrease the magnetizability of the myocardial tissue and the venous blood. And this can be done by using the T2 decay. So we want to have the arterial blood to be mostly unaffected, because the arterial blood has a much slower decay in terms of the transverse direction, and this can be achieved by using an appropriate preparation pulse. Now, if you do that, then you can get images like this one. So if you have a T2 preparation pulse, you get the image on the right hand side, and if you don't do that, you get the one on the left hand side. And you see that the contrast is just much better on the right hand side, and you can really see the arteries in a very good fashion. So just in case you don't know where to look at, so here you see the coronary arteries, and you see that here we actually have arterial blood, and in the ventricle we have here venous blood, and you see that the contrast is actually going down, and we have this very nice preservation of the contrast here of the arteries, and on the left hand image you can't see it as well. So this is a big advantage if you can work with these T2 preparation for getting better coronary images. What I already hinted at is that there is a difference in the local magnetization depending on the type of molecule that the hydrogen atom is actually in. So you can see if you have water, then our hydrogen is not in a strong binding. But if you have fat, you see that there is a very different local magnetic field. So in fat you have large molecules and high shielding, and this means there's a short T1. And in water you have small molecules and less shielding, so you have long T1 times. And this means that the resonance frequency differs, and this is then called the so-called chemical shift artifact. So there is a different resonance frequency in fat than in water. And we can use this effect to actually separate the two. So this yields then to water-fat suppression sequences. And if you don't apply a water-fat suppression or fat suppression, then you get images like this one here, where you see actually a very strong signal in the fatty tissues here. And if you have a fat suppression pulse, then you see that this bright ring is gone, and the contrast also remain mostly stable, but the fatty tissues are not as visible. Now that you can generate this difference between the two, then this allows for water excitation or water-fat separation. So an easy approach is then that you compute the water signal from this and the fat signal essentially by subtracting the two images, the fat enriched and the non-fat enriched, and this leads then to the decomposition into these materials. Very well. Of course, this can also be used for advanced purposes, and here you can see that you can also then quantify the amount of fat in the tissues by these separation techniques. So it's not just that you have pure water and pure fat in the voxels and they're entirely suppressed, but you can also then compute the percentage of the signal in that respective voxel, and this allows you to quantify really how much fat is in a particular voxel, and with this you can diagnose fat livers, for example. Now let's go to functional imaging, and a very cool technique is the so-called non-contrast angiography. And the key idea that is happening there is that you play with the actual imaging planes. So what you do is, if you have a blood vessel and this is the flow direction, so you're essentially exciting in this image plane, and then you depend on the flow. So the excitation will have happened at this point, but then you actually read out in this position here. And that's pretty cool, because if you essentially change the gradient of the readout, and this allows you to then detect whatever you excited here in this plane. So you use a different encoding scheme for the time of the readout, and this is giving you then images that will only be able to read signals in this direction. That's pretty cool, because then I have magnetically kind of tagged the blood and the blood vessel, but I don't need any additional contrast agent. It's not like that I have to insert iodine or gadolinium or something like that. I just use the magnetic properties of the blood itself and the excitation of the spins as a marker, and then very shortly later I read it out in a different position. And the only thing that is magnetized then in that particular slice is going to be the blood. So this then yields to very nice images, and here you see visualization of brain vessels, and this hasn't used any contrast agent at all. You just use a kind of magnetization plane, and then you measure in other slices the magnetization of the signal. So this is completely contrast agent free, and that's of course very good for the patient because they don't have to inject additional contrast agent. So there's more to that. There's also the so-called bold effect, and this is a key technique for functional MRI. And here we essentially use the effect that we can also measure the blood oxygenation in a similar way as we've already seen that for differentiating arterial and venous blood. The MR contrasts are dependent on the amount of oxygen in the blood. And if we know that, we can actually measure the areas where there's more blood or less blood in the brain. And this works at a rather short time frame, so it allows us to figure out in which areas of the brain more blood is deoxygenated. And this allows us then to figure out which areas of the brain are active. And this is of course a key tool towards understanding the brain in neuroscience. So if you look at that, you can then generate maps like this one, where you have a visualization of the brain and then you show a certain stimuli. With the stimuli, you can then figure out in which areas of the brain the most signal loss was taking place. And this allows us to understand where actually the oxygen in the brain was used. And this is essentially indicative of metabolism in this area. And this then allows for figuring out which parts of the brain were active. So if you then visualize these things, what is happening quite often, because the signal is rather low, it's not like that you can just pinpoint for a specific individual where the actual oxygen was used, but you need to do many measurements, and then what's often done is that you average over groups. And here you see that this is an average over males and females, and here they could identify a certain area that was activated differently in males and females for a specific stimuli. So here you have actually the difference during a 3D mental rotation task. So in a 3D mental rotation task, this particular area of the brain is used in a different way between male and females. So a very interesting technique that has been used very, very frequently in order to understand the brain and to get better insights in neuroscience. One of the key techniques. There's more. There's also diffusion weighted imaging, and in diffusion weighted imaging you can essentially figure out the orientation of the Brownian motion inside a volume, and this then allows us to estimate fiber directions, for example in the brain, and this leads to the field of connectomics. And connectomics are used to reconstruct the connections between the different brain areas, and there are indications that in specific diseases the connection between the areas is changed, and therefore the connectomics may be indicative of certain neurodegenerative diseases. Very well. This already brings us to the end of this presentation. So now you've seen also how we apply imaging in MRI. You've seen that we are essentially changing the gradient coils in order to introduce changes in the magnetic field that are locally different. We can use that for slice excitation. So with that we can read out a specific slice direction and only the voxels within the slice are excited. Then we can read them out, and in order to figure out in which location they actually are, we use an additional gradient before the readout to introduce a phase shift. And with the phase encoding, we could then interpret this as a kind of plane wave that is multiplied with all the excited voxels of that particular plane. And when we read out the signal, we are reading out the multiplication and the sum over all of these voxels. This we could demonstrate to be identical with an inverse Fourier transform, and therefore we can use the Fourier transform to reconstruct the measured image. So you can see that with these very elegant steps we are able to actually obtain image information from arbitrary plane directions. So you see this is a pretty cool effect, and with this we are able to measure very elegantly the entire human body in arbitrary orientations without any ionizing radiation. Yet we've seen that the disadvantage of this effect is that it's pretty slow. And in particular, if you have demands that you need images very quickly, you might want to use other kinds of modalities. And in particular, we want to start in the next video talking about X-rays, and X-rays are very, very commonly used, in particular in emergency situations, but also for acquiring bone and soft tissue contrast. So this is what we'll start talking about in the next video. Thank you very much for watching, and looking forward to meeting you in the next video. Bye bye.